Okay, in today's lecture, we're going to cover the section 5.1 material on eigenvectors and eigenvalues, which is going to be the main theme of our chapter 5 material. And you'll see this concept of an eigenvalue or eigenvector of a matrix appear in a lot of other classes. So there are some very nice applications for eigenvalues and eigenvectors. We're going to define them in this course, see how to find them, and then discuss some of the applications briefly. So let's consider the following sort of problem to motivate the idea behind an eigenvalue or an eigenvector. So let's suppose that we're considering a matrix transformation defined as x mapping to A times x. So this linear transformation can move vectors in a variety of directions. So if we think about a vector x in the plane, say a two-dimensional vector, when we apply this transformation to it, we've seen examples where it might reflect our vector about one of the axes, it might perform a shear, this might perform a scaling operation, and there are some special vectors for which this action of A is particularly simple. So to introduce that type of vector, let's consider the following example. Suppose that we have the 2x2 matrix A, and then two vectors u and v in R2, so two-dimensional vectors or vectors in the plane. And in part A, we're asked to find the images of these vectors u and v under the transformation where x is mapped to A times x. So to find our image of u under this transformation, we're going to take A times u. That's how our transformation is defined. Now here, A is the 2x2 matrix, 3, 2, 3, 8. And we're multiplying by the 2x1 vector u, which is 2, negative 1. So as our product, we get back a 2x1 vector, where our first row or first entry would be 6 minus 2, or 4, and our second entry would be 6 minus 8, which is negative 2. And then the image of v under this transformation would be A times v, so that is the matrix 3, 2, 3, 8, times v, which was the vector negative 1, 1. So we get back the 2x1 vector where our first row would be negative 3 plus 2, so negative 1, and our second entry would be negative 3 plus 8, so positive 5. So we found the images of these two vectors, and then in part B, we're asked to sketch those vectors and their images under the transformation where x is mapped to A times x. So let's start by sketching the original vectors. So here u was the vector 2, negative 1. So its representation would be the arrow whose initial point is at the origin, and whose terminal point is 2, negative 1. And then the vector v was negative 1, positive 1. So the vector whose representation is shown here. And now we're also supposed to sketch the images of these vectors under the given transformation where x maps to A times x. So we found that the image of the vector u, A times u, was 4, negative 2. So we have the vector whose initial point is at the origin and whose terminal point is at 4, negative 2, shown here. And then our image of v under this transformation was the vector negative 1, 5, so shown here. All right. Now in part C, we're asked to describe geometrically the action of A, this matrix, on the vectors u and v. So if we notice, when we look at the sketch of u and the image of u under this transformation, that they're scalar multiples of one another. So this vector, A times u, is twice the length of u itself. And we can see that in part A if we compare the components of these two vectors. So A of u was the vector 4, -2, which is exactly 2 times u, which was the vector 2, -1. So here we have a matrix acting on a vector, which is scaling the length of the vector by 2. So here we can say the matrix A times u is equal to twice u. So we have, as a description, scaling by a factor of 2. And in our second vector, we had v, which was -1, 1, and then A times v was this vector -1, 5. So we have a vertical shear. So we would describe A times v as a vertical shear by a factor of 5 here. All right. So the specific vector that we were considering, u, in this example, we saw had the following property. If we multiply the matrix A times the vector u, it's the same as taking the vector u and just multiplying by some scalar. So we're going to be considering these types of vectors throughout Chapter 5. Those are vectors where a matrix acting on that vector is the same as a scalar multiplication of that vector. So these types of vectors and scalars are given special names. So let's introduce some more terminology. We would say that a scalar lambda is called an eigenvalue of a square matrix A if there exists a non-zero vector x such that A times x is the same as lambda times x. So this scalar that we were multiplying by in the previous example to get the action of A acting on this vector is called an eigenvalue and is denoted as lambda. And the vector itself, which we're specifying, notice in this definition, must be a non-zero vector, is called an eigenvector of the matrix corresponding to the eigenvalue lambda. So when we're interested in finding eigenvalues or eigenvectors of a square matrix, we're looking for scalars or vectors such that multiplication of that vector by the matrix is the same as scalar multiplication of that vector. Now, we'll see in our next section a way to calculate these eigenvalues and vectors, but what we'll start by considering in this first section of Chapter 5 is whether a given vector or a given scalar is an eigenvalue or vector. So here I mentioned that it is easy to determine if a given vector is an eigenvector of a matrix. We simply see if multiplying the matrix by that vector would result in a scalar multiple of that vector. And it is also easy to decide if a specific scalar is an eigenvector of a matrix. If we look at our equation, A times x equals lambda times x, we just need to make sure that it has a non-zero solution. So let's look at some examples of these types of problems. In this first one, we're told to consider this 2 by 2 matrix A with vectors u and v given here. And we're asked, first off, is u an eigenvector of A? And if so, find the corresponding eigenvalue. So in order to determine if u is an eigenvector of A, let's look at the product A times u. So here, our matrix A is 7, 3, 3, negative 1. And we're multiplying by the vector u, which is 1, negative 3. So we get a 2 by 1 vector, where our first entry is 7 minus 9, so negative 2. And our second entry is 3 plus 3, or 6. And we notice that this product is exactly negative 2 times the vector u. So we've shown here that multiplying u by this matrix A is the same as multiplying u by a scalar negative 2. And that's the exact definition of an eigenvalue and an eigenvector. So we can say here that u is an eigenvector of the matrix A corresponding to an eigenvalue of lambda equals negative 2. All right. Now in the second part of this example, we're asked for the vector v, which is 2, 2. Would that be an eigenvector of this matrix? And if so, find its corresponding eigenvalue. So to test whether it's an eigenvector, we would take the matrix A times our vector v. So that is 7, 3, 3, negative 1 times v, which was 2, 2. And we want to see whether this product gives us a scalar multiple of v. So for our first row of this product, we have 14 plus 6, or 20. And our second row would be 6 minus 2, or 4. And we can see clearly that this would not be a scalar multiple of v itself. If we compare their entries, for instance, to get from 2 to 20, I would have to multiply by 10, but I see that if I multiply my second entry by 10, it does not give me 4. So these are not scalar multiples. And therefore, the vector v is not an eigenvector of this matrix A. All right. Now, one thing that, again, I want to stress moving forward through this section in this chapter is, by definition, an eigenvector is a non-zero vector. So recall that the zero vector is never considered an eigenvector for a matrix. So let's consider a similar problem where we're not given a vector, but we're given a scalar, say lambda equals 2, and we have to show that it's an eigenvalue of a particular matrix, and then find its corresponding eigenvector, or vectors. So we know that by the definition of an eigenvalue and vector, that the given scalar, lambda equals 2, would be an eigenvalue of this matrix A if and only if the equation A times x is equal to lambda, which was 2 times x, has a non-zero or non-trivial solution. Let's call it x. So let's see how we could test whether this equation has a non-trivial solution. Now the equation that we're working with is a times x is equal to 2 times x. So let's rewrite this equation a little bit. So that is, we would have a times x minus 2 times x would have to equal the 0 vector. So that is, if I just subtract 2 times x from both sides, I get the following equation, which is equivalent to the one we started with. And if I factor out a vector x, let's see what we're left with. So I would have a minus 2, but now be a little bit careful here. We would say times x is equal to 0. Now, we've got to be a little careful with our notation in this step because A is a 2 by 2 matrix. So when I'm subtracting this scalar 2, well, 2 is a 1 by 1 matrix, or simply a number. And recall that we can only add or subtract matrices if they have the exact same dimensions. So really, I can't just write a minus 2 here, but I would take a minus 2 times the identity matrix, which acts like a multiplication by 1 for the set of matrices. So now, instead of just subtracting the number 2, I'm subtracting 2 times the identity matrix, and we can define that subtraction here. So we've got to be a little careful when we're factoring out our vector x. Now, when we look at this equation, we have a homogeneous linear system, since our right-hand side is the 0 vector, and we need to know whether there is a non-zero solution. So to check whether there's a non-zero solution, well, there's a few ways we could do this. Let's consider the augmented matrix for this equation. So consider the augmented matrix. So here, our coefficient matrix is A minus 2 times the identity. So let's take a look at what exactly we're doing here. For 2 times the identity matrix, 2i, we have 2 times, now the 2 by 2 identity matrix is 1, 0, 0, 1. Here we're using the 2 by 2 identity since our matrix A is 2 by 2. And multiplying this by the given scalar, we have the matrix 2, 0, 0, 2. So we just take the matrix that has 2 on the main diagonal and zeros everywhere else. So for the matrix A minus 2 times I, we're taking the matrix A and we're subtracting 2 just from the diagonal entries. So that would give us 1, negative 2, 1, negative 2 for the first and second row of A minus 2i. And then we're augmenting this with the 0 vector. So we can see, of course, by examining this matrix that the 2 rows and the 2 columns are linearly dependent, which means that this matrix A minus 2 times I is not invertible. It's a consequence of the invertible matrix theorem. So if that matrix is not invertible, that means that this homogeneous linear equation or linear system has non-trivial solutions x. So we know immediately that 2 is indeed an eigenvalue of this matrix. And now to find the corresponding eigenvectors, we need to solve this equation for x. We want the form of the solution set for this equation. So to get our solution set, we could perform row reduction on our matrix. So here, taking row 2 minus row 1, we would have 1, negative 2, 0, and then a row of all zeros. So at this stage, our matrix is in reduced echelon form. It only has a single pivot. So there's one non-pivot column, which means we have one free variable. So here, our solution set would be the set of vectors of the form x is given by, well, if x2 is a free variable, we can see from our first row of this matrix that x1 is equal to 2 times x2, where x2 could be any real number. Or if we factor out that x2, we have the vector 2, 1. So our eigenvectors, well, or to summarize our work in this problem, let's write out our statement. So thus, lambda equals 2 is an eigenvalue of this matrix A with eigenvectors of the form x is equal to x2 times 2, 1, where x2 can be any non-zero real number. Now, why do we specify non-zero here? Well, if x2 were equal to 0, then for our eigenvector x, we would have the vector 0, 0, or the 0 vector. And recall the definition of an eigenvector is that it is a non-zero vector. So here we would have all the vectors of the following form, scalar multiples of 2, 1, where our scalar x2 is non-zero. So what we've established thus far by looking at our last example is the following. Lambda, the scalar, we would say is an eigenvalue of a square matrix A if there exists some non-zero vector x such that A times x is equal to lambda times x. And in our last example, we showed that we could rewrite that equation in the following form. A minus lambda times the identity matrix times the vector x is equal to the 0 vector. So we did that by simply subtracting a lambda x from both sides, and then factoring out an x, we have the matrix A minus lambda times the identity. So we need to know if this equation has a non-zero solution, that is a non-trivial solution. And we saw from our last example, well, if in order for this homogeneous equation to have a non-trivial solution, there has to be a linear dependence relation among the rows or columns of that matrix. And therefore, we would have a free variable as part of our solution, which means there's infinitely many solutions. So if we consider the set of all possible solutions of this equation, we could consider that as the null space of the matrix A minus lambda I, the set of all vectors x, which are mapped to the 0 vector by the matrix A minus lambda I. Now, we had shown in our chapter 4 material that the null space of a matrix is a subspace of Rn, here n, since our matrix A was an n by n matrix. And we would refer to this subspace as the eigenspace of A corresponding to the eigenvalue lambda. So by definition, the eigenspace consists of the 0 vector itself, because here we're considering the set of all solutions of this equation. So the 0 vector, of course, would satisfy this homogeneous equation. And then if we look at all of the non-zero vectors that satisfy this, those would be all of the eigenvectors of the matrix corresponding to that eigenvalue lambda. So let's think about what exactly an eigenspace might represent, or how to think about it geometrically. So in our last example, we found that the eigenspace consists, corresponding to the eigenvalue lambda equals 2, consisted of all multiples of the vector 2, 1. So if we think about what that eigenspace represents in the plane, since we were working with vectors in the plane, we would have a line passing through the origin in the direction of the vector 2, 1. So here in the x1, x2 plane, we would have our vector 2, 1 shown here. And we saw that any scalar multiple of this vector was also an eigenvector. So if we think about taking scalar multiples of this, well, we could consider all vectors in the exact same direction of lengths from 0 to infinity. So we could extend this line infinitely. Or if we think about negative scalar multiples of this vector, we would flip the direction of our vector and then could take all the vectors pointing in that direction of different lengths, depending on what scalar we chose. So we see that we have a line passing through the origin for a visualization of our eigenspace corresponding to lambda equals 2. Now for that last example that we had considered, we can also show that lambda equals 1 is an eigenvalue, and the eigenvectors are all multiples of the vector 1, 1, except for the 0 vector, but then the eigenspace also includes the 0 vector. So we would have a representation of a vector from the origin to 1, 1, and then looking at all scalar multiples of that vector, we would be defining a line through the origin for the eigenspace corresponding to this eigenvalue, lambda equals 1. So our eigenspaces here are spanned by a single vector, either the vector 2, 1 or 1, 1. So we see they're one-dimensional, or a line in the plane would be one-dimensional. So let's consider some other examples working with an eigenspace or determining an eigenvalue or vector of a matrix. So in this next example, we have the 2 by 2 matrix A, and we're told that an eigenvalue of this matrix is lambda equals 4, and we're supposed to find a basis for the corresponding eigenspace. So here, we are considering the equation A times x is equal to lambda, which was 4 times x. And we're looking for the solution set of this equation. That's going to be our set of eigenvectors. Now we saw that we could rewrite this equation as ax minus 4x is equal to the 0 vector, or equivalently as A minus 4 times the identity matrix times x is this 0 vector. And by definition, we're looking for eigenvectors, so we're looking for non-zero solutions of this homogeneous system. So as we did in our earlier example, let's consider the augmented matrix, which represents this equation. So here I'll say an augmented matrix for this equation is given by the following. So let's look at our coefficient matrix. Here, our coefficient matrix is A minus 4 times I. So we're taking this matrix A and subtracting 4 times the identity matrix, which would be the matrix which has 4 on the diagonal instead of 1, and zeros everywhere else. So subtracting 4 from just the diagonal entries of the matrix A, and we see we're subtracting 0 from the off diagonals, we would have a coefficient matrix of 6, -9, and our second row would be 4 and -6. And then we're augmenting this with the 0 vector, since this is a homogeneous system. So performing row reduction on this, we can get our solution set. So to simplify here, I could take my first row and divide through by 3. So that is 1/3 of my first row, which would give me 2, -3, 0. And if I were to take half of the second row, that is divide through by 2, I have 2, -3, 0. And again, we see our first and second rows are identical. Or these columns are clearly linearly dependent on one another. So there does exist a non-trivial solution, x, which is what we're looking for. And if we simplify a bit further here, we could, of course, take row 2 minus row 1. So I would have 2, -3, 0, and then a row of zeros. And if I put this in reduced echelon form, I would need a leading 1 for the first row. So to get a leading entry of 1, I could take half of the first row, and I would have 1, -3 halves, 0, and 0, 0, 0. So again, I've got my matrix in reduced echelon form. We see there's only a single pivot column, which means that our second variable, x2, is a free variable. So our solution set would be of the form x is equal to x1, which we can see from our first row, would have to equal 3 halves times x2, where x2 is free. So we would have a solution set of the form 3 halves x2, x2, or if we factor out an x2, I'm left with the vector 3 halves 1, where x2 can be any non-zero real number. Now, to make the form of this vector, which spans my eigenspace, a little bit easier, I want to eliminate the fraction within it. I don't like this 3 halves term. But I know that x2 is a free variable. It's going to range through all non-zero real numbers. So if I replace x2 with 2 times x2, then I could rewrite this in the form x2 times the vector 3, 2. And now this vector, 3, 2, no longer has entries which are fractions, but integer values. And as x2, my replacement, is allowed to range through all non-zero real numbers, we have exactly the same line that we would generate by using that first vector. So our eigenspace would be the set of all eigenvectors together with the 0 vector. And we can see that all of our eigenvectors are multiples of the vector 3, 2. Therefore, that vector would form a basis for the eigenspace. So let's say the eigenspace corresponding to the eigenvalue lambda equals 4 has a basis given by the set consisting of the single vector 3, 2. So here, since our basis consists of a single vector, we would say that this matrix has, or this vector space has dimension 1, or eigenspace. So let's look at another one, maybe working with a larger square matrix. So in this next example, we have the matrix A, which is this 3 by 3 matrix. and we are told that an eigenvalue is lambda equals -2. And as with the last example, we want to find a basis for the corresponding eigenspace. So as with the last example, let's think about what it means for -2 to be an eigenvalue. It means that taking this matrix A times a vector x gives us the same as taking the scalar -2 times x. And the set of all vectors x, non-zero vectors x that satisfy this would be our eigenspace. So let's consider rewriting this equation. We could rewrite this as ax plus 2x is equal to the 0 vector, or equivalently a plus 2 times the identity matrix times x is equal to the 0 vector. And we want to solve this system for non-zero vectors x. So let's think about our augmented matrix for this system. So here, in augmented matrix, would be the following. We're going to have a 3 by 3 coefficient matrix, a plus 2i. So let's think about how to get a plus 2i. So we're taking a and we're adding twice the identity matrix, which would be the matrix that has 2's on the main diagonal and 0's everywhere else. So really we're just taking the matrix A and adding 2 to the diagonal entries. So let's see what we have. Our diagonal entries will be 3, -1, and 3, and then all of the other entries remain the same. We're subtracting 0 from those remaining entries since the identity matrix has 0's everywhere outside of that main diagonal. And then we are augmenting this with our 0 vector, and we're looking for our solution set. So here, if we row reduce our matrix, we can show that this matrix is row equivalent to the following. The matrix 1, 0, -1/3, 0, 1, -1/3, and 0, 0, 0. We're still augmenting with the 0 vector. So it's not a difficult set of row operations to perform, but a bit tedious for a 3 by 3. So I'll skip that work here, but we can show that this is row equivalent to the given matrix in reduced row echelon form. So we see that we have one non-pivot column, which means that our third variable, x3, is a free variable. And our solution set would be the set of vectors x of the form where x3 is a free variable. And we can see using the first row of our augmented matrix that x1 has to equal 1/3 of x3. And using the second row of our matrix, x2 is also equal to 1/3 of x3. So if we factor out our free variable x3, we have the vector 1/3, 1/3, 1. Or again here, if we don't like these or these entries which are fractions, I could think about taking my free variable x3, which could be any non-zero real number, and I could replace it by 3 times x3 to get rid of these fractions. So this would be the same as x3 times the vector 1, 1, 3. So we see that our eigenvectors would be all non-zero multiples of the vector 1, 1, 3. So here a basis for the eigenspace would be the set consisting of the single vector 1, 1, 3. So again, we see that we have a one-dimensional eigenspace. Now, in certain examples, you might have an eigenspace of higher dimension, say if we had multiple free variables, where our solution set was a linear combination of two linearly independent eigenvectors, then we would have a two-dimensional eigenspace. Or we could see a three-dimensional and higher, just depending on what the dimension of our matrix is. So there are certain matrices where we can find eigenvalues very quickly. We'll see in general in the next section how to calculate eigenvalues for a square matrix. But one special case where we can calculate eigenvalues immediately is if our matrix is triangular. So this result is summarized by Theorem 5.1 from your text, which says that the eigenvalues of a triangular matrix are the entries on its main diagonal. So just like the determinant of a triangular matrix was the product of the diagonal entries, for a triangular matrix, the eigenvalues are the entries on that main diagonal. So as a quick example of this, we're asked to find the eigenvalues of each of the following matrices. And we can see that matrix A is upper triangular. All of the entries below that main diagonal are 0. So we refer to that as an upper triangular matrix. And since this is triangular, our eigenvalues would be the diagonal entries. So for matrix A, we can say the eigenvalues of A would be the values lambda equals 1, -2, or 4. And for our matrix B, we can see that it is lower triangular. All of the entries above that main diagonal are 0. So we have this lower triangular matrix. And so this theorem 5.1 says that the eigenvalues are the diagonal entries. So here, the eigenvalues of B are lambda equals 4, -3, and 6. All right. Now, another case where we might be able to find an eigenvalue of a matrix immediately would be the case where our eigenvalue is 0. So let's ask ourselves, what would it mean for the matrix A to have an eigenvalue of 0? So by definition, if we have lambda equals 0 as an eigenvalue, that would mean that taking the matrix A times some vector x would equal to lambda, which was 0 times x. And this must have a non-trivial solution. Remember, eigenvectors are non-zero vectors. Now this equation is equivalent to simply A times x is equal to the 0 vector, since any vector x multiplied by the scalar 0 would give us the 0 vector. So we know that this homogeneous equation has a non-trivial solution if and only if the coefficient matrix A is not invertible. That is, if it's singular. Otherwise, if A had an inverse, then we could solve this equation by left multiplying on both sides by the inverse of A, but we would have, in that case, x is equal to A inverse times the 0 vector, which would be the 0 vector. And we're looking for non-trivial solutions. So the only way we can have a non-zero solution is if A does not have an inverse. So we have the following results. Lambda equals 0 is an eigenvalue of the matrix A if and only if A is not invertible. So we have this new result, which we're going to add later to the invertible matrix theorem, that if A is invertible, then it would not have 0 as an eigenvalue. Or conversely, if the matrix A is not invertible, 0 is an eigenvalue. So let's consider an example of this. In this next problem, we have the 3x3 matrix A, where all of our entries are equal to 2. So it says here, without calculation, find one eigenvalue and two linearly independent eigenvectors of this matrix. So we can see here, since the columns and these rows are identical, they must be linearly independent. So let's start by saying clearly the columns of A are linearly independent. So that implies that A is not invertible by the invertible matrix theorem. And according to the discussion that we just had, that means that the value 0 is an eigenvalue of this matrix A. So here we found an eigenvalue, namely 0, and we were asked to determine two linearly independent eigenvectors. So to find eigenvectors, we're going to let A times x equal to lambda times x, which would be the 0 vector since lambda was 0. So let's consider that as an augmented matrix. We have the coefficient matrix A consisting of all 2's, and we're multiplying by some vector x and setting this equal to the 0 vector. So clearly, we can see this is row equivalent to the matrix 1, 1, 1, 0, with zeros in my last two rows. So that is taking half of the first row, and then rows 2 and 3, subtracting the first row we get here immediately. So we see that we have, in this case, two non-pivot columns, so we have two free variables. So our solution set would be the set of vectors of the form, well, we can let x2 and x3 both be free variables, and then using the first row of this augmented matrix, we see that 1x1 would have to equal negative x2 minus x3. Or splitting this, we can write this as x2 times the vector negative 1, 1, 0, plus x3 times the vector negative 1, 0, 1. So our eigenspace would be two-dimensional here. These two vectors, which are clearly linearly independent since they're not scalar multiples, would span our solution set for this system, or our set of eigenvectors, which is the eigenspace. So if we want specifically two linearly independent eigenvectors for this matrix, we could take these two vectors or any non-zero scalar multiple of those two vectors, since x2 and x3 were free. So to get our two vectors, let's take maybe v1 or x1 if you prefer, to be the vector negative 1, 1, 0, and x2 to be the vector negative 1, 0, 1. All right. So in the last part of this section, we will take a look at a result which is needed a little later in this chapter, and it's a very useful result when we start talking about applications of eigenvalues and eigenvectors, particularly in the study of systems of linear differential equations or difference equations, Markov chains. So when we consider some applications of eigenvalues and vectors, the following result, which is Theorem 5.2 from your text, is very useful. So let's take a look at what this theorem says. It says if we have vectors v1 through vr, which are eigenvectors of some matrix that correspond to distinct, so those are all different eigenvalues, lambda 1 through lambda r, of some square matrix, then that set of eigenvectors, v1 through vr, is linearly independent. So what this theorem says is as long as your eigenvalues of a matrix are all distinct, so all different numbers, then the corresponding eigenvectors will form a linearly independent set. And this has a lot of nice applications. So let's take a look at the proof of this theorem. So this will be a proof by contradiction. So the way that this works, the result that we're trying to establish is that the set is linearly independent. So let's assume the contrary. So let's say here, suppose that our set of vectors v1 through vr is linearly dependent. And based off this assumption, we're going to show that a contradiction arises, so they must be, in fact, linearly independent. So if we have this set of vectors, which is linearly dependent, and they are by definition eigenvectors, that means that none of these are zero, then we can make use of a result we had earlier in the course, namely Theorem 1.7, which says that one of these vectors can be written as a linear combination of the others. So that means there exist scalars, let's say C1 through CP, such that one of these vectors can be written as a linear combination of the first p. So let's say C1 times V1 plus C2 times V2 up through CP times VP is equal to, say, VP plus 1. So one of the vectors from our set is a linear combination of the preceding ones. Now, for reference, I'm going to call this equation 1. We're going to come back to this equation a couple of times. So if we take this equation and we multiply by the matrix A, let's call it the n by n matrix in our problem, we have A times this linear combination, C1, V1, plus C2, V2 up through CP, VP is equal to A times VP plus 1. But now using the commutativity of, or a distributive property of matrix multiplication, I can distribute my matrix A, and I have C1 times A V1 plus C2 times A V2, and so on up through CP times A VP is equal to A times VP plus 1. But recall that these vectors that we're considering, V1 through VR, were eigenvectors of a matrix with the eigenvalues lambda 1 through lambda r. So that means that if I take the matrix A and I multiply it by one of my vectors, let's say Vi, that's the same as taking lambda times Vi, where the eigenvalue lambda is the ith one, so let's call it lambda I. So each of these expressions where I have A times V1, A times VP, or A times VP plus 1, well, that's the same as just taking lambda 1 times V1, or lambda P times VP, or lambda P plus 1 times VP plus 1. So I'm going to reference this equation as equation 2. And now let's consider another related equation. If we were to multiply my equation 1 by the eigenvalue, lambda p plus 1, we have the following. So taking equation 1, multiplying through by lambda p plus 1, we have C1 lambda p plus 1 times V1 up through CP lambda p plus 1 times VP. And on the right-hand side, we would have lambda p plus 1 times VP plus 1. So I'm going to call this equation 3. Now, by subtracting equations 2 and 3, let's see what we have. So in equation 2, we had the following, and then we're going to subtract these corresponding expressions in equation 3. And by grouping like terms, we can see if we factor out a C1, we would be left with lambda 1 minus lambda p plus 1, all times the vector V1, and so on, up through, if I factor out a CP, I'm left with lambda p minus lambda p plus 1 times VP. And that's equal to, on the right-hand side of equation 2 and 3, we had the exact same expression. So taking the difference, we're left with the 0 vector. Now, we had assumed that this set of vectors, V1 up through VR, were linearly dependent. So any subset, V1 through VP, would also have to be linearly dependent. Which means that all of these weights, or here, the vectors which we're considering V1 through VP are linearly independent vectors. Since the first vector for which we could write this as a scalar or a linear combination of scalar multiples of these vectors V1 through VP was VP plus 1. That means the first P of them must be linearly independent. So here saying since these vectors V1 through VP are linearly independent, that means that the only way we could take a linear combination of these and get the 0 vector is for all of these scalars to be 0. So we'll say all weights in this linear combination must be 0. However, we know that these differences, lambda 1 minus lambda p plus 1, lambda 2 minus lambda p plus 1, and so on, up through lambda p minus lambda p plus 1, cannot be 0 because we were told that our eigenvalues were distinct. So none of those eigenvalues are the same number. So we'll say here none of the expressions, let's say lambda I minus lambda p plus 1 are 0, since the eigenvalues are unique, or distinct, excuse me. So now that implies if the differences of those eigenvalues can't equal to 0, then all of these constants, C1 up through Cp, must be 0. So we would say all of these C1 through Cp values are equal to 0. But then, referencing equation 1, we would have the vector Vp plus 1, which was the linear combination C1, V1 up through Cp, Vp. Well, if all of those constants are 0, then this vector, Vp plus 1, must be the 0 vector. But this is impossible. So we could say this is a contradiction. Since this vector Vp plus 1 is an eigenvector. And by definition, eigenvectors are non-zero vectors. That means that our initial assumption must have been incorrect, that the set of vectors was linearly dependent. So we've established that our set of vectors V1 through VR are linearly independent. So again, this theorem that we're concluding with has some very nice implications when you start talking about applications of eigenvalues or eigenvectors in solutions of systems of linear differential equations or difference equations.